Hello, welcome everyone. I am Mr. Smith here to talk to you about gases today as we work through our chemistry unit. So thanks so far for doing all the work and tutorials and videos that you've watched so far. Before our final review, which I guess is a practice test more than anything else, we're going to work on this Chemthink. So we're going to go to the website that I'll make available for you. And then when you're done, you're going to post your problem set success to the Edge Elastic. So make sure your name is over here in the guest. And then you can't do the problems until you do the tutorial. So you really want to do the tutorial and then the problems all together, even if it takes you 2 or 3 tries to get it done. Because once you leave this page, you're going to have to redo the tutorial just to get back to the problems. All right, so this is going to be 36 slides about gases. Get myself a little bit out of the way. So we're going to bring in some gases and then really make as many observations as possible. Maybe get a couple more gases in there. Looks like they collide off of each other. They collide off the walls. They speed up when they hit each other kind of from behind. They slow down when they hit head on. The larger molecules are moving slower, and so the larger molecules, argon, just based on the periodic table. Argon has a molar mass, let me look it up, almost 40, neon almost 20, and helium 4. So here comes a small helium. They tend to move faster. What else can we do? Heat it up. And we can kind of see they all speed up a bit. If I slow it down, if I cool it down, they all slow down quite a bit. So temperature is involved. The mass of the gases has an effect on it. And again, they just kind of collide off each other quite a bit. So those are some of the observations that we've kind of made here. And now we're going to go ahead and try to answer those questions kind of one at a time. So here I am. The speed of the atom depends on the temperature. Well, that's true, because the higher the temperature, the faster it went. Different types of atoms move at the same speed as long as they were at the same temperature. So that's false, right? Because we saw some of the heavier atoms go slower and the smaller atoms went faster. So correct. Lighter atoms move slower. That's false. Heavier atoms move slower. That is true. No pattern between them. No, we saw the pattern. In a sample of one type, all the atoms move at the same speed. So that was false as well. Some went faster, some went slower. And I can't click here again to re-show it to you. I think I can go back this way. Here we go. So are they all going the same speed? And while it's tempting to say that, some are hardly moving at all, and some are now going pretty fast. And that's really a temporary condition until they hit. And so now, again, some are going much faster than others, some are going much slower than others. So even though they're all, in this case, helium, all at the same temperature, some gas particles are moving slower. So I think we have to redo these again. Speed of atoms depends on temperature, true. Different types of atoms move at the same speed, false. Heavier, slower. One type of atoms all move at the same speed, so that was false as well. There is kind of a range of possibilities here. There will be a mix of speed in any gas sample. That is why we refer to the average speed of the atoms. And that speed is pretty high, about 1,000 miles an hour. So this doesn't really even show the accurate speed. And though all those collisions create pressure. Pressure is the force we feel over a specific amount of area. So PSI is what we tend to use for bicycle tires and car tires. So pounds per square inch. So the atmosphere that we're feeling right now is roughly 5 pounds per square inch. So every inch of our body is being hit by about 4.7, or generally 5 pounds. And so this actually says 15. So I think I said that wrong. I said 4.7. I meant 14.7. So I'm glad I was corrected. So about 14.7 pounds per square inch. That is a fairly large number, but your body's used to it because we're always that way from the moment we were born until now. We're always feeling it. In fact, when the pressure changes dramatically, things like our ears pop, so we can feel that coming. So over here, watch gas sample for a minute. What is creating the force on the sides? And so here's a PSI pressure meter that can detect the pressure, a pressure sensor, and it's those collisions of those gas particles. The force is caused by the impacts of the atoms with the sides of the container. A huge number here. So this is how many gas particles are hitting your hands very often. Each second, it's this many. So this is a ridiculous number, right? There's 1,000, there's 1,000,000, there's a billion, trillion, quadrillion. What's after quadrillion? Pentillion, hextillion, septillion. Maybe I got that right. So that's a huge number. This is happening every second, every inch, every second, and they're all moving at about 1,000 miles an hour. So these are the big numbers. Even though gas particles are so small, there's so many of them hitting you so fast. We get 15 pounds, which is definitely something that we can feel. So what makes pressure and why? So those are the collisions. So we're going to see temperature change a bit. An increase in temperature, if I take the reading, up goes the pressure. These are going faster, so there's a new data point. And the colder temperatures give me lower pressures. You can see a lot less collisions over here. So I'll bring this all the way down, take a reading, low. And so what we see is this correlation between pressure and temperature. So this is what I was looking for here. So high pressure, high temperature, low temperature, low pressure, high and high, and low. So that's a direct relationship over here. So they even kind of show you the animation here, a big P versus big T, small p, small t. And it just goes up and down this diagonal line. Why are they? So scientists like to make explanations. Now we're actually getting kind of these highlighted collisions there. And so if you were actually able to count these collisions, it's a fair number. But if I heat it up, now these collisions with the walls are happening more often. And not only more often, but more forceful since they're moving faster. And even more so, the pressure is high, and now there's just a constant stream of multiple collisions. But the other extreme, which is kind of a nice way to compare things and learn about things, is look at it through the extreme. Not that many, or I'm still probably 2 or 3 a second, but this is probably a dozen a second. And so cold temperatures, less movement, less collisions, therefore less pressure. High temperature, a lot of speed, a lot of collisions, a lot of pressure. So we're going to try to come up with these two statements. There are more collisions with the sides. Each collision is more forceful because the atoms are moving faster. So here's a bit of a drag and drop. So as we increase the temperature, that causes an increase in speed. And that does two things. Increase in the collision force. It'll go there. Increase in frequency. There we go. Increase in collision force. And both those things, kind of by definition, give us an increase in pressure. So now we're going to look at something else. Now it's going to be looking at the amount of atoms we have. So let's take a reading. There's our starting point. Let's add in some helium. 1, 2, 3. Take a reading. More pressure. We saw pressure go up here as well. 1, 2, 3. More pressure. Let's take out, I added 6, let's take out 7. 1, 2, 3, 4, 5, 6, 7. There you go. All right. Take a reading. Take out some more. Take a reading. See how many we can add. Take a reading. Again, we see this direct correlation between number of atoms and pressure. So we can see this straight line, up and down. There we go. Up and down. A lot of atoms, a lot of pressure. Not a lot of atoms, not a lot of pressure. Not only graphically, but over here as well when you count those collisions. Again, this is another direct relationship. So with more gas particles, you can see many more collisions with the walls of the container. If I take out these gas particles, all but one, a lot less collisions with the walls of the container, and we can see that with a very small PSI number. But more atoms gets me more collisions. Again, sometimes it helps to look at the extremes. There are more collisions with the sides. More collisions by definition gives you more pressure. So increase in atoms causes an increase in number of collisions, which causes an increase in pressure. All right. So here we're going to work with pressure and volume. So let's take a reading, and then we can contract this a bit. Notice the pressure's going up. Notice the pressure's going up over here as well. Here's the smallest one that we can get, and here's the biggest one that I can get over here. So again, it's all about those collisions. When there's less space for these gas atoms to move around in, they collide with the wall more often. When there's more space, they collide less often. And so I think I can move this. Yep, just up and down. Again, a big P, now it's a small v. So this is an inverse relationship. The other ones were a direct relationship. So with a lot of space, we don't have as many collisions, and so we have a low pressure. With not a lot of space, we get a lot more collisions, and so we have high pressure. You can watch this dial here, kind of dial back to a low pressure or squeeze it into a high pressure. So we have an inverse relationship. Okay. So again, inverse relationship. There are more collisions on the side. So as volume decreases, more collisions with the sides. More collisions means a higher pressure. If I pull this back, as you count the pressure, little explosions, not nearly as many. If I squeeze it in, many more bits of pressure. I think I went so far past it, went over. So let's maybe go as far as this. So there's a pressure, and I can pull it back, and now there's less pressure. So a decrease in volume leads to an increased number of collisions, which by definition is an increase in pressure. So there's these four variables that are tied together: pressure, temperature, volume, and moles. They're actually in one equation. It will be the combined gas law or the ideal gas law, but all four of these variables are tied into one another. So we are done here. So you can go ahead and try the problems. And so this time you have to get 15 right before you get 3 wrong. So really kind of pay attention to the wording of it all, to check all that applies, and kind of remember all the chemistry that we've taught you. Thanks so much for your time. Good luck. And remember, chemistry is everywhere.